The normal distribution is one of the most common distributions that we see in statistics. It can be used to model individual observations from certain natural processes. It can also be used more commonly for modeling statistics themselves. So this distribution will actually be one we see quite frequently throughout the rest of the course. But during this introduction, we're going to focus on a particular context where the normal distribution fits the data quite well. So if we were to take a sample of brush-tail possums, that is those cute guys there, and we were to take measurements of their heads, so how long their head was, what we'd actually find is that the mean of this distribution is about 92.6 millimeters, which is a little bit under 4 inches. And if we were to look at the standard deviation of those, the lengths of their heads, we'd find that the standard deviation was about 3.6 millimeters. And importantly, the distribution of the head lengths would actually look quite symmetric about the mean, and it would also be more of a bell-shaped curve if we were to plot the histogram of the data. The data would actually fit quite well with the normal distribution. Now, one thing that's important to realize is that the normal distribution is not a perfect model for any natural process, but it's oftentimes a good approximation for particular contexts. So there's many different contexts where it will not work well. For example, if the distribution is going to be skewed. But there are some particular contexts where the normal distribution does pop up, and it tends to pop up more often than other distributions. So if we were going to say this was our distribution of brush-tail possums, we might have the center noted at 92.6 millimeters. And then if we mark our standard deviations about there, and out here, then we'd have about 89 millimeters. We'd have approximately 96.2 millimeters, and so on. So let's suppose that we are looking at a particular possum, and we observe this possum has a head length of 98 millimeters. We want to know how many standard deviations above the mean is the possum. So we know the possum is above the mean because the center is at 92.6. We also know it's above 1 standard deviation above the mean. And if we actually calculate the next one up here, we'd have 99.8. So we know it's somewhere between the first and the second standard deviation. So if we want to actually figure out, approximately where that possum falls, we should first look at the difference from the observed value, 98 to 92.6, and that's going to give us 5.4. And then, since we're trying to figure out how many standard deviations above the mean this possum is, we're going to take 5.4 and we're going to divide it by the standard deviation, so 3.6. This is going to come out to 1.5. So this particular possum with the head length of 98 millimeters is 1.5 standard deviations above the mean. Let's do one more example. Let's take a possum with 89 millimeters. So for this possum, let's draw the distribution one more time. So these drawings are actually really useful to kind of get a sense of what's going on. So this very rough drawing is actually quite useful. So then, actually, if we look back up to our top line here, we have 1 standard deviation below is actually 89. So this particular possum will be 1 standard deviation below the mean. We could also do the calculations of this as well. So let's actually go through the calculations for this one too. So if you actually wanted to verify that, we could take our possum, our 89 millimeters for head length, subtract off the mean, 92.6. That's going to give us negative 3.6. And now we want to divide by the standard deviation to get the number of standard deviations that the possum falls below the mean. So negative 3.6, negative 3.6 divided by 3.6 is negative 1. So what's important here is that there's actually this negative sign in here. And if you notice, before what we did is we also subtracted the mean from the value that we were observing. And we're doing this again here down below with the 89. So again, we're taking our observed value, we're subtracting off the mean, and then we're going to be dividing by the standard deviation. And this gives us the number of standard deviations our observation is away from the mean. And the sign of that value there tells us if it's above or below the mean. So a positive value would mean that it's falling above the mean. A negative value would mean that it's falling below the mean. So here we have a possum with 89 millimeters is 1 standard deviation below the mean. So the formula that we're actually using here is pretty important. What we're actually doing here is that we have our observed value, which we're marking as x. We're subtracting off the mean, and then we're dividing by the standard deviation. So this tells us the number of standard deviations x is above or below the mean. And this formula is actually quite important. This formula is called the z-score. And this z-score formula is actually useful for a variety of contexts. So while we're going to use it here in the context of the normal distribution, you can use it for other contexts, but we won't be able to do the fall-among calculations that we're going to do next. So again, you can use the z-score for other distributions, and it just tells you the number of standard deviations your observation is above or below the mean. But again, for other distributions, we will not continue on with the next calculations we're going to do in the context of the normal distribution. All right, so let's hop onto a new sheet here. So now what we're going to do is we're going to ask the question, how many possums have a head length smaller than 98 millimeters? And once again, don't worry too much if your normal distributions don't look too perfect. It's perfectly fine. You just need a very rough sketch to be able to take advantage of drawings like this. As before, we've still got our center at 92.6, and we're looking for possums that have a head length smaller than 98 millimeters. So again, 98 millimeters was out here. And just as a reminder, we have our mean of 92.6 millimeters, our standard deviation of 3.6 millimeters, and here we have our x value of 98 millimeters. So as before, what we had actually done before, we're going to still use. So we're going to still use the z-score. So we're going to have our 98 minus our 92.6 divided by our 3.6. And this was our 1.5. And so thinking about our question, how many possums have a head length smaller than 98 millimeters? So that's going to be represented by all the possums that would be falling down here. So we're looking for that particular area. Since the possum is above the mean, we know that at least half of the possums are going to be below, and it's a pretty good chunk. It looks like it's a pretty good majority of the possums are going to have head lengths smaller than 98 millimeters. So what we want to do is we actually want to use this z-score with either a normal distribution table or statistical software to figure out what is the area below 98 millimeters in this distribution. And so just using the z-score, what we can do is we can look up the z-score of 1.5 in our table. And also it's worth noting that it's 1.50 basically. So we're going to always generally use 2 decimal places for the z-score. At least if you're using a distribution table. And if you're using a distribution table, you can look in the row that has 1.5 for the start of the z-score. And then you can look in the column that has a second decimal point of 0. And what you're going to find at the intersection of that row and that column is that this is going to give us a value of 0.9332. And this tells us actually the fraction of the possums in the population that are falling below the 98 millimeters. So for a normal distribution, the fraction of the distribution that falls below 1.5 standard deviations above the mean, so falling below a z-score of 1.5, is 0.9332, so 93.32%. And we can do a similar calculation for our other possum. So remember our other possum, we had an 89 millimeter head length, and we want to look at the fraction of possums with head lengths smaller than 89 millimeters. So again, if we draw our normal distribution, it's going to be centered at our mean, 92.6, and we have our possum with the head length of 89 millimeters. And so we're looking for the possums with head lengths smaller than 89 millimeters. So that's going to be down here. And if we, again, use our z-score, so if you recall from before, the z-score for this one was -1, so this is -1.00. And if we look up this in our z-score table, what we're going to find is that if we look in the row where it's -1.0 and the column where it's a second decimal of 0, we're going to get a value of 0.1587. So that's what that area is, 15.87%. So let's say that we also wanted to determine the fraction of possums that had head lengths between 89 millimeters and 98 millimeters. How many possums are we going to have that meet that criteria? So just like what we've done before, what we want to do is we want to draw a picture. So we have our mean at 92.6. We have our 98 millimeter up here. We have our 89 millimeter down here. And we're curious about how many possums fall in this region here. How many possums fall with head lengths between 89 millimeters and 98 millimeters. So if we want, we could actually, what we could do is if we can find area for the upper cutoff, subtract off the area for the lower cutoff, then that's going to equal that area that we're actually interested in. So from our earlier examples, what we can do is we can actually grab our 0.9332, subtract off our 0.1587, and then we get 0.7745. So this is actually the fraction of possums that we expect to fall between our 89 millimeters and between our 98 millimeters. So far what we've been doing is we've been taking our summary information, so like our mean, our standard deviation, and our observation. We've then been plugging it into the z-score formula to get the number of standard deviations that the observation falls above or below the mean. And then we use that to get the lower tail area. And we can, again, do this step either through a table or software. Software is definitely becoming more common now. What we can also do is we can also run into problems where we're looking for the observation at a particular percentile or at some other place on the distribution. So let's say that we have a question of how big is the possum's head at the 90th percentile. So to do that, again, just as before, the first thing that we should ever do is draw a picture. So we have our distribution. We have our mean at 92.6. And what we're doing is we're looking for some value up here where the area below is 90%. So we need to figure out basically what is this x value. We don't know what that x value is. And it maybe isn't obvious how we get that, but what we actually do is we look back up here. What we did is we had our lower tail area, and we're actually going to work backwards now. So we're going to get the z-score, and then we're going to go back and we're going to get x using the z-score. So we can look up 0.900 in the table, and we're not going to see exactly that value, but we're going to see a value very close to it. And so if we look for the closest value, the closest z-score in that table, corresponding to the 90th percentile, we're going to get a z-score of 1.28. So now that we've got our z-score, we know our mean, we still know our standard deviation, but we don't know x. But we can use the z-score formula to find it. So again, we have our z-score formula of x minus the mean divided by the standard deviation, and we're just going to plug in some values now. So we have our 1.28 for our z, and we have our unknown value x, we have our 92.6 for the mean, and we have our 3.6 for the standard deviation. And if we would solve for x, we get about 97.2 millimeters. So 90% of possums have a head length less than 97.2 millimeters. Let's do one more. Let's say we're interested in the 30th percentile. And again, to start, what we always do is we draw our graph. And as always, it's not that big of a deal if it looks great or if it just is a very rough sketch. So we have our 92.6 in the middle. And what we're doing is we're looking for a value where about 30% of the distribution falls below that value. So we know we're going to be below the mean, since the mean is at the 50th percentile, since it's a symmetric distribution. And so maybe it's somewhere around here. So we're looking for, so we know that we're going to say there's 30% there. And we want to find what that x value is. So thinking back to before, we have our kind of system that we have before. We have our mean, our standard deviation, our x. We go get the z-score, and then we get our lower tail. And again, here what we're doing is we're going backwards. So what we need to do here is we need to figure out what our z-score is. So what we can look this up in a table, and if we do, what we're going to find is that the closest z-score is approximately negative 0.52. And this negative is very important. We can't forget the negative. And now we know we have our mean and our standard deviation, and we just don't know x. So we're going to use our z-score formula. We're going to plug in our values. Again, don't forget the negative. That's very important. And we're going to have our x, our unknown value x. We have our 92.6 for our mean. And for our standard deviation, we still have our 3.6. And what we get is x is about 90.7 millimeters. So this step here, where after we got our z-score, and going back through the z-score formula to solve for x, that's just going backwards. So we have these two ways that we can use the z-score formula. We can take, if we have our known cutoff value, we can take our mean, our standard deviation, and our cutoff value, we can get z, and then we can get the lower tail and do any additional calculations we need to. Or what we can do is we can figure out what our lower tail is. In this case, we're using a percentile, so we know the lower tail is 30%. Then we use either our table or our software to figure out what z should be. And then we're solving using the z-score formula for what x is. So this is a pattern that you'll see for a lot of normal distribution problems. And whenever you're in doubt about what to do, write down this structure here and think about, do you have a tail area that you're working with, or do you have your cutoff values and you're trying to get to a tail? You're going to be working in one direction or the other direction. One last topic I want to touch on briefly is some kind of standard values corresponding to the normal distribution. So if we have our normal distribution, so there's some general rules of thumb to know about the normal distribution. The first one to know is that within one standard deviation, we have about 68% of the observations. So about 68% of the observations for a normal distribution fall within one standard deviation of the mean. And if we think about two standard deviations, so going out to those two standard deviations, we're going to find that about 95% of the data falls within two standard deviations of the mean for a normal distribution. And lastly, the last important statistic to keep in mind, that is a good rule of thumb to have, is 3 standard deviations. 3 standard deviations out, it's about 99.7% of the data will fall within those 3 standard deviations of the mean. So it's very rare to see observations that fall further than 3 standard deviations out, at least if just looking at a very small number of observations. If you look at a lot of data, we're going to find that about 0.3% of it will fall 3 standard deviations out or further if the data actually are normally distributed. And if the data aren't normally distributed, these rules of thumb won't apply. So again, just to recap, we have what is basically called the 68, 95, 99.7 rule. And again, just convenient things to know. That's all for this video. If you enjoyed it, please give it a thumbs up below. And if you want to see more videos from OpenIntro, please subscribe. Thanks for watching.